Hey guys, Vex here. Um, so it's been a while since the last time I've done a tutorial for you. It's because it's a little bit hard and tricky. Basically, I don't have the most capable computer to do video recording, and I don't live in the most quiet place in the world. So it's a little bit tricky, yeah. But I really wanted to make this video and share it with you because recently I've been working on a garbage collection free string alternative that would allow us to do the most common operations we do on string, but without any allocations, basically, like format, concat, append, yeah, same as concat, substring, replace, and stuff like that. So this is what I have. I called it gstring. Now G is short for garbage collection free, so GC free string, but I thought that was a little bit long, so I just called it G string. But then I noticed that, wait a minute, isn't that the women's panties thing? G string. And I was, yeah. But then, like whatever. Like we always name things stupid ways. Like this is what we do as programmers. Like take for example the word unsafe. I think it's the worst naming you could think of. It should be called unmanaged. Um, then you have float. Like what is a float? Like you're floating in midair or something. And then you have like mono behavior. Like what is this? Like a mono speaker, stereo speaker, whatever. So let me show you some cool stuff now. So I have two samples. I have this test script just to measure allocation for my for gstring versus string, and then I have the same operations done in both samples. So we've got format, concat, substring index of, last index of, replace, to upper to lower, things like that. And then we have an intern test here, which we'll talk about in a minute. Well, let's just see. Let's just run, see the profiler. Let me just make sure I'm recording. Okay. Now you'll get a memory hit when you first start the game. We'll talk about that in a bit. But if we take any sample like from here and go to our behavior update, we'll see that gstring took 0 bytes, allocated 0 bytes, string allocated 1.2. So half kilobyte for format took 0.03 seconds. Or yeah, seconds, or milliseconds I should say, not seconds. Our format took 0.01, so it's a little bit faster. Some operations are a little bit slower, like replace, a little bit slower, but it's okay because gstring is optimized for allocation and not speed, at least at the moment. So let me go over and let me just put a few breakpoints just to make sure that we're getting the right results from these operations. So we have format, so number equals 1, 2, 3, float equals that, and string equals that. Now I decided I'm only going to support ints and floats and strings and booleans in my format. You can have up to 10 arguments. Concat, index of, like we take a substring from the index of period to the end, so we get the extension, then we get the file name, replace, pretty straightforward stuff, replace string, and I'll talk about intern in a bit. To upper to lower. Oh, come on. Jesus. Okay. And yeah, so it's pretty much the same operations done in string. But the difference is that we're garbage collection free. Now, how do we do this? How do I do that? Well, for basically three or a couple of things come into play. We use unmanaged or unsafe or unmanaged, basically pointers, to mutate strings. So that's key, so that we don't allocate strings when we do any operation. We have strings in our cache that we get and mutate, and then when we're done with them, we basically dispose of them. So we have a string cache, or I should say gstring cache. This is the cache that we use to get strings to manipulate and then return. And then we have an intern table. This is useful. I'll talk about why it's useful in a bit. But basically we have a dictionary, the key being numbers, integers representing string length, so 1, 2, 3, 4, 5, stuff like that. So each, and then the values are basically stacks. So you have a stack of gstring. Now the stack is going to have a predefined capacity, let's say 32. And each gstring in that stack will have an initial value of x. I just decided to go with x because it makes it obvious that this string is not used or disposed. So in this case, it's going to have, each string will have like 3 x's. Okay, so now if we do gstring sir equals John, what we do is, well, first of all, notice that the length of John is 3. So we go to our cache, we go to this entry, go to the stack, and request a string. So we'll get a string that looks like XXX. Once we get that, we do some memcpy stuff, basically pointers to copy the values from John over to this. So this XXX will become John. And then we mutate that string. This is the string that we mutate. We don't mess with the input. Right, because if we mutate this, we'll be messing with the intern table, and that will give you some really weird results. Like, let me show you. So if we look at this test here, this is basically a console app in my Visual Studio. So I have a text saying hello, and then I define a pointer to that text and set PDR, the first character, to X. I print out text, and then I print out hello. Now if I look at this, you know, like intuitively, I would think that the first output would be xzello, basically XELLO, and then the second one is just hello, because I'm printing out the literal hello. Right? This is what I would expect, but if you run this, you'll get Zello in both statements. So basically you're mutating the intern table of C#. If you don't know about the intern table, just look it up. It's basically a table of strings. So every time you mention the literal hello, it's gonna give you back the same string. It's not gonna allocate a new string and give it back to you. Otherwise, this wouldn't be a problem. But basically these two strings here, they're pointing to the same object. So basically there's like some sort of a dictionary of string. So the table at hello equals hello. So if you mutate that, change it to Zello, now the table becomes table at hello equals Zello. So every time you mention the word hello, you're gonna get Zello. So this is why it's important not to mutate the input that you get, but to get a string from our cache and then mutate that. Okay. Now I should mention that gstring internally uses a string. This has a prefix size. This size doesn't change. I just change the content of that string. Okay. Now every string in that cache is meant to be disposed of. So every time you get you do, gstring equals John or whatever, you should dispose of this string so that it goes back to the cache and gets disposed of. But if you look at my test, there's nowhere in my test that I'm saying, gf.dispose or something, or get it back to the cache or something. This is where this block comes into play, and the iDisposable pattern, which is actually one of my most favorite patterns or features in C#. Basically, you say using gstring block, and then this block will basically it stores a stack of gstrings. So every time we do an assignment, every time we get like a gstring, we push that string to the stack of that block, so that by the end of this block, we'll be disposing of all the stacks that were in our block. I don't know if that made sense, but let's just see it. Why did I break in here? Let me just break in here. So we've reached the end of the block. We're gonna execute our dispose. Now if I look at my stack, you'll notice it contains all the strings that we've used. In that gstring block. So this block serves the purpose of keeping an eye on every gstring assignment, so that when the block ends, it does the disposal for us. Now when I dispose, I basically get the stack that corresponds to my length. So I'm disposing of this hello has a length of 10. So we're gonna get the stack right here. We push ourselves into that stack, and then we basically zero ourselves out by copying over this character over ourselves, just to indicate that we've been disposed of. So now the value is xxxx. Okay. Now the stack has the cache has an initial capacity of 128. You can override those values by using initialize. Where is it? Initialize. Come on. Okay. You can call initialize anywhere from your game and override these capacity variables, so it's no big deal. Like if you know that you'll be needing more, if you need more than the default values, you can use initialize. So this is the initial cache capacity, this is the initial block capacity. So how much gstrings can fit in a block? Like this is the initial capacity. So once you've gone over it, actually no. Wait a second. Yeah, no, when I allocate my blocks, I do block capacity multiplied by 2. So actually the amount of strings that initially goes into this stack is block capacity multiplied by 2. But the capacity of my blocks array, or my blocks list, or my block stack is 32. That means that you can have 32 nested blocks, basically. Like, you could say, using gstring block, you can keep doing that. Now, when you reach 32, basically the stack will be empty, and I will return a new block. And then when you dispose of that block, it goes back into the stack. So allocations happens once, basically. But I might go with something else, like something higher. Like, I think I should go with, I don't know, maybe multiply by 3 or 4, basically. But I'm not sure about the numbers. Like, I'm just experimenting with things right now. But yeah, this is the initial intern capacity, our intern table. Yeah, I should talk about intern now. Now, notice every string by the end of the block will get disposed of. Now, what if you had a string in your class and you wanted to store the result of some string operation, like concat or whatever? Like, what if I wanted to store the result of this concat to this string variable? Well, what's going to happen? If we look at our inspector, we'll see that the string has garbage values. But if we break and look at it, you see it has a right value. What is going on? Well, basically, when this block ends, the gstring that we use to calculate the result, this result will get disposed of. So this will point to a disposed gstring. Now, to avoid that, we use this intern method, which basically says, you know, calculate the result of this operation. So we're gonna get a string that is the result of this concatenation, and it's basically gonna say, if this value is contained within this intern table, return it. Otherwise, allocate a new string. Copy the values over. This is the key. We're copying the values over, so that when we dispose of the G string, it doesn't affect us. So we allocate a new string, we copy the values over, and we add it to our intern table, so that the next time we request the same value, we just get it back from the intern table. This is like a similar idea to C#'s intern table. Now, if I look at this string browser, gstring browser, and look at the intern table, this is what it has. This is the content of my intern table, and it has the string that we entered in here. So if I like manipulate with this, you see it allocates a new string because it didn't find the string in the table, so it allocated a new one. Like, you see. Now, the nice thing about this is that you could pre-intern stuff in your game. Like, you could have, like, when your game runs, like, maybe you want to intern, I don't know, like this. Maybe you use this a lot in your game and you don't want it to allocate at runtime, so you pre-intern it, which basically means if you ever, if at any point in your game you came across value plus I, like, let's say let's say you have a dictionary and you're populating it, just like the dictionary we have in here. So we're populating it with items. So item as 0 equals 0, item is at 1 equals 1, stuff like that. Now, this is interned at runtime, but what you could do is just say, let's say you're not gonna have more than 10, no, 100. So you intern gstring intern item plus I. So if you ever come across this point, item concat I has already been entered, so this won't allocate. This will just look up the table and give you your item, right? So this is one thing you could do. Yeah, so that's about intern. Yeah, so that's pretty much it. You could look at the implementation. I have some notes here. I'll be sharing it soon. You can look at the public API. So you have length, initialize, block, intern, get hash code equals toString, which returns the internal string value. Implicit operators between bool and gstring. Implicit operators between int and gstring. I do some basic math stuff, like I count the number of digits, see if it's negative. If it is, I prepend the minus sign, and then I do an int cpy thing, which basically does a module to get the rightmost digit. So if I had like 125, so 125 module by 10, I get 5. So 5 plus 48, which is the base, which is the ASCII code for 0 character, the character 0. So I'd get the character for 5. And then I divide that by 10 to get rid of 5, so I have 12. I do the same thing over and over again and populate my string that way. If you know a better way, let me know. Same thing for floats. Well, similar thing. I basically calculate the numbers at the right, at the left side of the decimal point, and then at the right side, according to some decimal accuracy value that you specify. By default, it's 3, which means if you give me a string, a number like this, I will give you back a string of no more than 3 digits after the decimal point. Yeah. So I pretty much had to re-implement the string class with my own implementation, like my own insert, my own remove, stuff like that. I mean, I had a blast because I was using pointers. Like, it's been a while since I've used pointers, so it made me happy. Yeah. Concat, now I recommend that you use the static version of concat, this one, because it enforces the cast to gstring. Like, whenever you do any concatenations using gstring, I recommend you use this version, because if you say gstring equals, value plus other whatever, this is not guaranteed to be concatenating via gstring. In fact, I think this is a string concatenation. So we're concatenating to a string is using the default string concat, and then we're assigning the result back to gstring. Now you might get away with it if you explicitly cast the first value to a gstring, so that way it will use gstring concat. But why would you put yourself in that position where it's not so clear which version of concat you're using? So I recommend you use this one. And like I said, for format, it takes up to 10 arguments, and they're all gstrings. But since we've provided implicit operators, conversion operators between integers and floats and bools and strings to gstrings, it's not a problem. You can pass in integers and floats in here as well, which means you can add support to things like vectors and stuff like that. Yeah, the last thing, I just want to drive home the idea of intern. Like, you only want to use it if you want to store the result of your gstring operation. Like here, I'm populating that dictionary. Like let's say I don't intern. Like, let's see what happens. Right now it has the correct values, but if we wait for it to reload, yeah, see, garbage. This is because the result, the gstring that we've used to construct the keys, are now disposed. So we need to intern it. Okay. Like I said, you could either intern in place or pre-intern everything before, at the start of your game. Is there anything else I want to say? Yeah, that's pretty much it. Oh yeah, one thing here. Let's suppose that the initial stack capacity was 4. So basically, we're requesting hello. So we're gonna go to this entry, to the stack at that entry, and pop it. So we're popping it once, twice, third time, a fourth time, and then the 5th time, well, we've already popped it 4 times, so the stack count is 0. So what's gonna happen then? Well, if you ever pop it and the stack count is 0, if you get the stack and the stack count is 0, I'm gonna allocate a new gstring. And you have this log thing here, so you could hook it up. So I say gstring log equals debug log. So when the allocation happens, it's gonna give me a feedback. But then the thing is, when the block ends, we're gonna push these strings back to that stack, so that the next time we start the block, we're gonna pop once, twice, third, fourth time. The 5th time, we already have 5 elements, because previously when we disposed of these strings, we pushed them back to the stack. So now we don't have to allocate again, right? Let me show you. I don't want my update to run. I don't want to run at all. Okay. So I'm requesting 5. I'm requesting hello 1 2 3 4 5. So these are 6 characters. So let's see. Come on. Okay, so I'm gonna run my test. So this is the first hello. The stack count is 4. That's fine. This is the second hello. The stack count is 3. Third hello 2. Fourth hello 1. Fifth hello 0. So we allocate a new string for that length. But then the thing is, once we're done and we dispose of our block, we'll notice that our block contains 5 elements. So when we dispose of them, we'll end up adding the 5th string we added back to our stack. So the next time we start the block, the stack will have a count of 5 and not 4, right? So if I look at the stack, it's got a count of 0. Next time it's got a count of 1, 2, 3, 4, 5. Okay. If I go back to Unity and look at my console, I see this stack equals 0 allocated in string. That's okay, we already saw that. But then if I execute it again, it doesn't allocate because the stack now has a count of 5. Okay, let me get this back. What was that? 48. Yeah, like I said, I'm not sure about these values. Like right now I'm just experimenting and seeing what works and what doesn't. Probably I'll be releasing this as a DLL, and the source code will be on JIT. If you do want to take the source code and use it in Unity, you need to go to your assets folder and basically have these two files, gmcs.rsp, smcs.rsp with the values, with the unsafe argument, and then make sure you restart Unity, and that's it. Yeah. So yeah, see you later.